Picture a room in the late 1960s, buzzing quietly with typewriters clacking and cathode ray tubes flickering. Researchers huddle over early computers, trying to teach machines not just data but meaning. One program, plucking apart ambiguous English sentences, pauses. Can it really grasp our tangled language, or is it fumbling in the dark? That tension between raw code and true understanding sets the stage for a bold experiment in artificial intelligence. Language isn't just words, it's riddles wrapped in context. So how do you build a machine that can untangle those riddles? In 1968, a team led by Ross Quillian designed a program that could take a sentence like, "I saw the man with the telescope," and figure out exactly who was holding what. It sifted through possible meanings, ruling out unlikely ones until it locked on the right interpretation, an early glimpse of computers parsing human nuance. Think of this process like peeling an onion. Each layer reveals new clues. The program built internal models, creating mental maps where words connected like streets on a city grid. These connections helped the machine weigh probabilities and resolve ambiguity, much like how your brain guesses the right meaning before you finish a sentence. This wasn't just a clever trick. It transformed how we think machines might understand us. From simple word puzzles, these experiments cracked open the possibility that computers could grasp context, not just strings of text, a step closer to real AI dialogue. Logic seems straightforward, right? But real-world problems toss in contradictions and fuzziness. What happens when crisp logic hits messy reality? One standout experiment addressed how machines handle conflicting info. For instance, if a house is described both as large and small, the program doesn't just throw up its hands. Instead, it flags inconsistencies and explores which interpretations might still hold, mimicking human reasoning when facts don't perfectly align. Imagine navigating a foggy path with a lantern. The program uses analogies like stepping stones. If you recognize a pattern from one situation, you apply it to another, even if details differ. This flexible thinking helps machines make leaps, not just follow rigid chains of logic. The payoff? Machines begin to handle real-world messiness, adapting instead of failing. This keeps AI usable in unpredictable contexts, from natural language to problem-solving, a hint at how human intelligence thrives in ambiguity and partial truths. If you want a machine to learn, it needs an inner model of the world. But how do you build a mind from scratch in silicon? The book highlights experiments where programs don't just spit out answers. They build internal models representing objects, actions, and knowledge. One example, a system that understands a physical scene by piecing together elements like walls, doors, and people, forming a mental map akin to your brain's spatial sense. Think of these internal models as mini worlds inside the machine. Each concept is a building block, linked tightly to others, enabling the program to rehearse scenarios or predict outcomes, like a chess player imagining moves ahead or a driver visualizing a route before starting. This method laid foundational blocks for modern AI. By capturing not just data but structured meaning, these models allow machines to learn adaptively and engage in complex reasoning. It's the quiet birth of thinking machines, still shaping our tech today. Remember that flickering screen in the 60s lab? Those early struggles to read ambiguous sentences weren't just tech trials. They were the birth pains of machines learning to think. Semantic Information Processing shows us how carefully layered logic, clever analogies, and internal models came together to craft the earliest minds inside machines. Next time you get tangled in unclear text, try building your own mental map, just like those pioneering programs did. Subscribe for more book summaries like this one.